Hi everybody. So this first lecture will be on review, hopefully mostly. So the first thing we want to look at here is functions, which is something you probably studied in your previous classes, but this will be the main thing that we study in this class. So you want to make sure that you have this down, and these seem like things that you probably are pretty familiar with. But just make sure that you really get things down, because sometimes people aren't as maybe familiar with these things as they think they are. Um, so, um, so the first section we're going to look at then is section 1.1 on functions and their graphs. So you might remember that sometimes you can represent functions with graphs by working in, say for example, the Cartesian coordinate system, or something like that. So let's first of all define what a function is. So remember, a function from a set D, which is sometimes called the domain, to a set Y, which is sometimes called the range, is a rule or something that assigns a unique or single element of Y to each element of X, right? So that means in order to be a function, each element of X can only get sent to one element of Y. So if you think that in terms of a X and Y coordinate system, right, that means each X coordinate can only get sent to one Y coordinate. You can't have, say, for example, an X coordinate that's sent to, say, 3 and 5. Again, you can think of a function as a machine where you put in some input number, some value of X, the machine does things to it and you get an output. Like if this is the function X plus 1, the function just takes whatever you feed in there X and then just spits out a 1. To help you also visualize this, so let's say you've got the domain, which is a set of numbers, and the range, which is a set of other numbers. And again, these don't necessarily have to be numbers, but so remember, you can have two different values in the X coordinate and get assigned the same Y, right? So you can have two X values get assigned the same height, but what you can't have is an individual X values assigned, say, a height of 3 and a height of 5. So here's some examples of some functions in their domain. So remember, the domain is the set of X coordinates that the function sort of has domain or control over, the set of X coordinates where the function can tell it where to go. So there's the sort of if you think in terms of the machine, right? Some numbers you might not be allowed to put into the machine because they don't give you a finite real number in the range. So for example, if you have like the square root of X, for example, its domain is 0 to infinity because it doesn't make sense to take the square root of -1. So the function y equals x squared, right? Remember, that's sort of a parabola, right? That its domain is -infinity to infinity. It'll cover the entire x-axis, right? In other words, no matter what number you stick in for x, if you square that number, you'll get a value for y. But because you're only getting positive values here, remember the range or the output values are only 0 to infinity. For 1 over x, again, you can stick any number in that you want as long as you don't put 0 in for x. And then the range in this case will be from -infinity to infinity, excluding 0. For the square root of x, again, remember you can't put negative numbers in. And again, you only get numbers from 0 to infinity, right? Remember the graph of the square root of x looks something like that. Here again, if you wanted to solve this, if it's hard to solve, just take 4 minus x and set that greater than or equal to 0 and solve it. You'll get that for the domain. And then again, this is just the graph of this, except you're not shifting it up or down or anything, right? I guess you could also think of this as the graph of x shifted 4 to the left, but then also flipped around the x-axis because the x is negative there. For this one, again, you can't have things that are negative inside the square root, so that means that x has to be some number between -1 and 1, and again, the range there will be between 0 and 1, right? You can only get values between 0 and 1. If x is, say, for example, 0, you get 1, and if x is 1 or -1, you get 1. And so this turns out this will be the sort of the top half of a circle of radius 1. But you don't have to visualize these necessarily, but remember, you can visualize functions with graphs. So again, here's an example of a function, right? Y equals x plus 2, right? Each x coordinate only gets assigned to one y coordinate. In this case, the domain for any linear function is the entire x-axis. So I should maybe mention back here that for the domain here, I may sometimes use, for -infinity to infinity, I may use the symbol for real numbers instead. That just means you can put any number in for that you want. So the domain for this would be all real numbers, and then so would the range, because the line goes up and down forever, right? Remember, you can think of the domain as the shadow cast by the function onto the x-axis, or imagine that the function is made up of a bunch of beads. If you push them all on down to the x-axis, right, that would cover the entire x-axis, and then the range is what you get if you push the beads over onto the y-axis, right? Again, you would get everything from negative infinity to infinity. So this is an infinitely long line. I obviously can't graph the whole thing, but that would be an example of a function. Just to remind you too that if you do have a particular function, especially if you're using function notation, I mean, we might use, let's say, y is equal to x squared, but we could also use function notation, which is probably preferred. I'm not saying this is the graph of x squared, but just remember, if you put a number in for x, right, that tells you the height that the function goes to, right? So you can think of that as the y coordinate. So as an example, right, with a parabola, I guess we already looked at this. If you were to graph it, and again, you can do this by just plotting points, you might already know what this looks like. But you can see we do have the domain and range that we saw in the last couple slides, or a couple of slides ago, because again, it does cover everything from negative infinity to infinity, and it goes from 0 to infinity. As a more applied example, let's look at some data from a tuning fork. So maybe this is the time, and this is the pressure exerted by the tuning fork on the air. If you were to plot that, you would see you would get sort of a parabolic, or a trigonometric curve there. So that would be another example of the function. Remember, in order to be a function, you have to satisfy the vertical line test. So if you have something like this, this is not a function. And remember, things can be made into functions. Like you can take this relation and then just split it up into two pieces, right? If you solve this equation for y, right, you'll get 1 minus x squared, or y squared. And then just remember, when you solve, you have to take the square root of both sides. So you actually get the square root of 1 minus x squared, which gives you the top half of the circle, and then negative square root of 1 minus x squared, which gives you the bottom half of the circle. Here's another function that you might be familiar with. The absolute value function. Remember, it gives you a v-shaped thing. And if you forget what a function looks like, right, hopefully most of these you have memorized. Remember, you can always plot points, right? If x is 0, y is 0. If x is 1, y is 1. If x is 2, y is 2, etc. Right? If you have negative 2, you've got 2 there for y. You might also have what's known as sort of a piecewise function, or sometimes called like Frankenstein functions, because they're kind of pieced together. So, for example, on this part of the domain, you have y is equal to negative x. Then between 0 and 1, the graph has the behavior of y is equal to x squared. And then after that, to the right, forever, you get the function of y is equal to 1. We'll come back and take a look at those later. But let's look at maybe some examples finding the domain and range of a function and graphing it. So again, for something like this with square roots, the main problem is, again, you want, if it's in the domain, you want the thing inside the square root to be greater than 0. So just go ahead and set that greater than or equal to 0 and solve, and then that's your domain, right? So in this case, the domain would be everything from 3 to infinity, right? And you can write it like that, or if you'd rather write it as, that way too, that's fine. As far as the range, well, this is just the graph of the square root of x, and if you think about the lowest value you can take is 0 when x is 3. So in this case, the range, the minimum value it could take would be 0, and then as you make x larger and larger, you can take the square root of any number that you want, right? Or again, you could just say x, or I guess y in this case, since it's the domain, is greater than 0. So remember, one of the main things you need to worry about when you're dealing with the domain is you can't have negatives inside square roots. Another thing is you can't divide by 0. So in this case, the domain would be x can't be 2, because if you put 2 in for x, you get 0. Again, you could also write the solution this way: negative infinity to 2, union 2 to infinity. I don't care which way you write it. I think it's more efficient to write it that way, but whichever way you want to write it is fine. And then the range in this case would be everything from negative infinity to 0, union 0 to infinity, because if you think about it, there is no number you can stick in for x that will make this fraction 0. Or again, if you'd prefer, you could just say y can't be 0, right? Whatever's easier for you. Okay, so there's some examples of finding the domain and the range. Now another function that we want to deal with is something called the greatest integer function, and this has different notations here, so I didn't really write this down here, but it's sometimes denoted by that. I think in your book they use this notation, or I've maybe seen like this notation also. But so the greatest integer function will give you the greatest integer that is less than or equal to the number inside the symbols. Right? And this is sometimes called the floor or step function or staircase function. You'll see why here in just a minute. Basically because if you graph it, it looks like a staircase. Right? So the idea is any number between 0 and 1 gets assigned a height of 0. So positive numbers essentially just have the integer part stripped out. So if you have like 1.23, that gets assigned a value of 1, right? The greatest integer function of 2.56 is 2, right? Because 2 is the largest integer that is less than the number inside the brackets, right? Kind of a confusing name, but that's how it works. Now for negative numbers, you got to be a little bit careful though, right? For like if you have negative 1.23, the largest integer that is less than this number is actually negative 2, right? So basically all the numbers between 0 and 1 will get assigned a height of 0. All the numbers between 1 and 2 will get assigned a height of 1. All the numbers between 0 and negative 1 will get assigned a height of 1. So it forms sort of this staircase thing. And we aren't going to use this very often, but this is something you might run into in some of your computer science courses or something like that. So just something to be aware of. Now you can also have the least integer function, and sometimes the notation looks like this, or might look like this, or you might see something like an int, and then with the star down here to indicate that this is the least integer function as opposed to up here, but it gives the smallest integer that is less than or equal to x. This is sometimes called the ceiling or step function or staircase function, again because it sends the value sort of up to the ceiling instead of down to the floor like the last example. So the graph of this will be very similar to the graph of what we had before, but right for the greatest integer function, right, remember all the numbers between 0 and 1 get assigned a height of 0. They're sent down to the floor, sort of, if you think about it that way. Or with the least integer function, right, they're assigned the integer that is greater than the number in the bracket. So all the numbers between 0 and 1 get assigned a height of 1, but you still get this typical staircase shape. So another thing we want to look at is where is a function increasing or decreasing. This kind of makes sense, common sense, but let me define this, right? So a function is said to be increasing if the height that x sub 2 gets assigned to is greater than the height that x1 gets assigned to whenever x is less than 1, right? So in other words, if you have two values, say x1 and x2, as long as the height of this point is always greater than that, then it's increasing, right? So if you're walking uphill to the right, then you're increasing. And then similarly, when you're walking downhill, you're decreasing, right? So if you have f of x sub 2, that should always be greater than f of x sub 1, right? For any thing where x sub 1 is some number to the left of x sub 2. So this kind of just makes kind of common sense with regard to our notion of when a function is increasing or decreasing, right? It's if you imagine that you're walking on the curve from left to right, right? If you're walking this way, right, then the function's increasing. If you're walking downhill, the function is decreasing. Remember, you can also have even and odd functions. So a function is even if it equals its mere reflection or on the x-axis. Some examples of an even function would be like the cosine function. So you might remember certain identities like cosine of x is equal to cosine of negative x. Now some examples of odd functions would be like the sine function. So remember sine of x is equal to sine of negative x. And also any functions with just odd powers in them, right? If you have like x cubed or whatever, will have that property. Remember, you can test symmetry for a function about the x and y axis. You can either have symmetry in this way or you can have symmetry about the origin. Remember, when you add a constant to a function, that'll shift it up or down. I'm just kind of going through some results there here that hopefully already you know. Remember that we talked about straight lines and slope. We'll come back and talk about that more later. Remember a line that's horizontal like this, where you have is an equation of the form y equals a number, whereas a vertical line would be x equals a number. But remember, that would have a slope of 0. Here are some common toolbox functions that you should have memorized, and make sure you memorize these well enough that you can match them on the curve or on a graphing. situation. So there's a lot of these we've already looked at. Like here's the straight line y equals x. That just goes through the origin. The 45-degree angle here. Here's y equals x squared, y equals x cubed, y equals x to the 4th, x to the 5th. I don't know if you need to worry about these so much, but just remember if the power is odd, right, it looks kind of like the graph of x cubed, and if it's even, it looks like the graph of x squared. Here's some other toolbox functions that you should know. The function 1 over x. Maybe there's one other one I should put on here too that I don't see, which is y equals the absolute value of x, right? I guess we kind of already looked at that. Remember, that's sort of a V-shaped thing like that. Here's some other functions. The graph of 1 over x squared looks like this. Graph of y equals 1 over x squared looks like that. Here's the square root of x, cube root of x, y to the 3 over 2. I don't know if these last two are quite so important, but they wouldn't hurt to memorize those. I'll probably let you guys bring a formula sheet or a note card or something for most exams. So you can certainly put this stuff on there if you want. So again, here's just sort of a summary of the common toolbox functions. Again, I know I don't have all of them listed, but there's sort of an idea. Now remember, in terms of other functions, right, remember we don't just have the toolbox functions, but we have lots and lots of different other types of functions like polynomial functions, right? Remember, a polynomial is something where the power on the variable or variables can't be negative and it can't be a fraction, right? So the exponents have to be positive whole numbers, or they can be 0 also. But one thing to remember about polynomial functions is that if you do graph a polynomial function, the function should be nice and smooth. There shouldn't be any sharp corners like the graph of the absolute value of x or something like that. So if you're graphing a polynomial function and it turns out not to be smooth, something's wrong there. Other types of functions that we may have looked at would be rational functions. Those are functions where you have a polynomial divided by a polynomial. And remember, the weird thing with these is you can have these weird asymptotes in here if the bottom is 0. These get kind of complicated to graph, but we will maybe do some of those. You can also talk about other algebraic functions, functions that can be defined in terms of an equation. These are just some examples. But the idea, basically, one of the main things that we'll look at in this course is if you have a function like this, being able to find the slope of the curve at any point, right? So for a lot of curves, the only thing that you really know how to find the slope of is a straight line. It will turn out that eventually we'll be able to find the slope of some function like this at any point that we want. Remember, there are also transcendental functions, functions that can't be written in terms of a finite number of subtractions, divisions, multiplications, things like that. For example, the sine and cosine functions, exponential functions. So I'm just kind of going through some of the stuff we've looked at before. Logarithmic functions. I also talked about piecewise functions, right? Remember, for something like this, you could have a function like this that's defined in different parts on different parts of the domain. So for example, when x is less than 0, right, this would just be the equation of 3x minus 5, which would be a straight line that goes through -5 on the y-axis and has a slope of 3. So you can draw the whole thing if you want, but remember that you only get the graph to the left of 0, and then once you hit 0, you switch behavior and the graph jumps up here to 4. And remember, the graph of x cubed looks something kind of like this, but you don't want to draw that part, so I don't know exactly what the graph is going to look like, but something like that. And I'm not expecting your graphs to be perfect or anything, but for piecewise functions, right, you might have to graph them a piece at a time. One last thing I wanted to talk about here is proportionality problems, because this does involve functions of the form, say, y equals kx, or y equals k over x if you have an inverse proportion. But these are all functions. Even this one, even though you might divide by 0 when x is 0. But let's look at a specific example, right? So let's say the kinetic energy of a mass is proportional to the square of its velocity, right? So what you're basically saying is that the kinetic energy, let's call it k. Well, maybe we should call it E, because we'll maybe use k for a constant. So it's proportional, right, which means you can take a constant, let's call it k, times the square of its velocity, right? And you call this whatever you want. You can maybe call it c for constant. I'm just going to call it k because that's normally what they do. So let's say that we know that the energy in this case is 12960 joules. You don't have to worry so much about the units. And the velocity is 18 meters per second. What is K when V decreases to 10 meters per second? Well, the first thing we need to do is find K by solving this equation, and then we can plug that in with the 10. And you can kind of use your intuition with this, or kind of ballpark this if you can before you do the problem, right? If you think about it, if you're decreasing the velocity, that should substantially decrease the energy, right? So in this case, if you go ahead and solve this for K, right? So we expect a much smaller value for the energy in this case. If I take 12960 and divide by 18 squared, I do get the kinetic energy drops to about 23805.43. Okay. So there's an example of where you could use functions to solve proportion problems or things like that. You might also have some functions or some problems like this that are slightly more complicated, where you have to derive the function on your own, right? In the last example, we were kind of given the function. But let's say that you want to express this the y-coordinate of this point P. So imagine that this point P here can move back and forth, and as it does so, right, it changes the length and width of the rectangle here. You want to express the y-coordinate of P, in other words, the height here in terms of x, and then write the area of the triangle in terms of x. And this is one of the main things we'll do in calculus is you might have a situation like this where things are changing and you want to maximize or minimize things. Like maybe you'd like to find the dimensions, the height and width that would maximize the area of the rectangle. Well, in this case, the height of the triangle, in this case, if this distance is x and this is 1, can be given by the Pythagorean theorem. So the height of the triangle here is basically 1 squared plus 1 squared, right? If this distance here is 1, I guess it's an isosceles triangle. I guess we're looking for the length of this here first, right? So so the height of the triangle again should be the square root of 2. So in this case you'd have the height squared, so this distance, which we don't know, squared, plus this distance here, which is 1 squared, should equal the hypotenuse, which has a length of square root of 2 squared. So if you solve that for h, you'll get h is equal to 1. Maybe just to do that over here, right, you'll get h squared is equal to, or plus 1 is equal to the square root of 2, which is 2. So if you subtract 1 from both sides, you'll get h is 1. So h either has to be plus 1 or minus 1, and since we're dealing with a height, it has to be positive 1. So the equation then for the height of the point is given by that. So the area of a rectangle, right, is basically equal to the length times the width, and here we're going to use this length and this width, so we'll have to double it. So basically take 2 times xy using the y that we just figured out here, which is that the height of the point is at negative x plus 1. So that means that this would give you the equation for the area of the rectangle. And then, for example, if you wanted to find out the maximum area here, right, this would be a parabola, you could maybe find out where the vertex is. And we'll see that there are other ways of doing that using calculus that might be more efficient, but you guys don't know that stuff yet. So, okay, so hopefully that gives you guys a pretty good introduction to 1.1. If you have questions about the video or anything, don't be afraid to ask. And remember, you can always stop and rewind the video at points if you want, or if you need a point of clarification, don't be afraid to contact me about anything. Okay, so I hope that makes sense. If you guys need help, don't be afraid to contact me.